Good morning, everybody, and thank you for joining us. I'm Rebecca Santa Maria Fernandez, Director of Industry Partnerships and Commercialization Engineering at Imperial's Enterprise, and I'm delighted to welcome you to our first Imperial.Tech.Pitch event with a focus on transition to zero pollution. With these events, we are truly hoping that we can bring to your home offices, in your living rooms or sheds, or in your office at work, some of the amazing work that goes on at Imperial. Our mission is not just to understand the world, but to have an impact on it, to change it for the better. And for that, we need innovation. And innovation needs enterprise. Enterprise at Imperial brings researchers, students, and businesses together to inspire and empower one another, unleashing some of the brightest minds who are determined to solve some really important challenges. Impact is really at the heart of what we do. And today, I really hope that we give you a snapshot of the research capabilities and amazing technologies that we're working on that will support and enable the transition to zero pollution. We cannot keep this to ourselves, and we actually need you and your organizations to help us change the world. First, you'll meet my colleague, Professor May Ryan, who is leading on Imperial's Transition to Zero Pollution initiative. She'll tell you a bit more about it. And then you get to meet our 6 speakers that will showcase our research and technologies that they're working on. Right after the pitches, you'll have time for a Q&A chaired by Professor May Ryan, and I would encourage you to submit your questions or comments via the chat function so that we can pick these up during the Q&A. After the event, our team will be more than happy to follow up with you, help you get access to our researchers and inventors, also understand a little better or get more information about their research and technologies and see how those might be relevant to you and your organization. Contact details are in the event page and also in the chat. I truly hope that you enjoy the event, and I'll hand you over now to Mary Ryan.
Thank you, Rebecca. Good morning, everyone. I'm Mary Ryan. I'm the Vice Dean for Research in Engineering here at Imperial College, and I'm a Professor of Material Science in the Faculty of Engineering. And it's my great pleasure to chair this meeting today. So today we're here to talk about Imperial College's new initiative, the Transition to Zero Pollution. This is our new vision to realise a sustainable zero pollution future, going beyond carbon to treat pollution in all its form and take a systems-based approach to really thinking about what a future clean, sustainable society could look like. To deliver this, we know we're going to need really strong partnerships between research, industry and government. And so we hope that you are going to be keen to join us in this initiative. Building a future that's free from human-made pollution is going to require a radical shift in all aspects of our industry. It's going to require us to develop and deploy new technologies. And this initiative is also going to require us to bring together people from across the college and beyond. We need to talk to engineers, fundamental scientists. We need to think about human health and the environment and business models and policy making. We really want this to be a holistic vision, a zero pollution mindset, if you like, that's going to create and translate holistic socio-technological solutions to pollutions in all its forms, going beyond carbon, thinking about the climate crisis, and thinking about a future that we do it right. So a key priority in this initiative for us is to really make sure that we deliver impact on the research that we do. So that means we need very strong partnerships with industry and government, and stakeholders that really help us inform the challenges that are out there and what the barriers are, and then help us translate the solutions that we develop in the college to direct impact in industry. So today we're going to talk about some of the potential solutions and some of the challenges that we know we face in getting towards a zero pollution future. You're going to hear from some researchers at Imperial about thinking about materials that support green energy solutions. We're going to think about deploying technology into infrastructure and products to make them more sustainable, and thinking about how we might monitor real-time pollution emissions. I'm looking forward to hearing our brilliant researchers give their talks on these topics, and also to joining you for the Q&A session at the end of the talks. Please remember to submit your questions into the chat as you're listening to the talks and as we go through the Q&A. All right, without further ado, it's time for our first pitch.
Hello, my name is Jamie Spears and I run the White Paper series at the Sustainable Gas Institute, which is a part Shell-funded institute here at Imperial College. Earlier this year, we published our 5th white paper, The Flexibility of Gas, What's It Worth? And I'm going to present some of that now. Gas is a very interesting energy vector because it delivers energy with significant variation over seasonal and daily timescales, as shown in the two figures here. However, in the future, we might use significantly less gas as we try to meet increasingly challenging climate targets, which raises questions for how useful this flexibility will be in the future. Now, natural gas networks provide flexibility through a number of different mechanisms, including varying production and varying the pressure in gas pipes, something we call line pack, essentially using those pipes as storage. Conventional forms of storage like underground geological storage, and imports of gas through pipelines and LNG markets to other countries. In the future, we might have other mechanisms to provide flexibility, increasing the competitiveness and the value of flexibility in gas networks. And one of the interesting outcomes of that increasingly competitive flexibility is that it appears as though the cost of meeting seasonal demand has been reducing over time. That's true in a number of countries, and the data here shows that for the UK, where the difference between the summer and winter gas price appears to have been decreasing over time. And one of the interesting knock-on effects of that is that conventional storage has been becoming less and less competitive, and as a result we've seen the closure of a significant volume of storage across Europe. Now, this raises a number of challenges for future gas networks. In order to make gas networks relevant in the future with increasing climate targets, we might want to do things like putting low carbon hydrogen in those gas networks. One of the outcomes of that would be that the amount of energy that we can store in pipes or in underground storage sites would reduce, and that would essentially increase the cost of these types of storage. And adding to that is the fact that in the short term at least, hydrogen networks are unlikely to have the ability to import hydrogen from other countries through pipelines or through other types of market arrangements, meaning that hydrogen networks will have to rely on storage as their way of meeting flexibility. That might mean that flexibility is a more expensive proposition in the future for low carbon gas networks. And that's definitely something that's of relevance in planning out future energy systems in a world where greenhouse gas emissions are significantly constrained. Now, there's a significant amount of more detail in our full report, which you can find on the website, and there's also a policy brief that can be found there. Thanks very much for your time.
Hi, my name's Mark Stetler, and I'm based in the Department of Civil and Environmental Engineering at Imperial College London. What I want to do in the next couple of minutes is just emphasize the need to understand aerosols and their contribution to pollution. So firstly, what is an aerosol? Well, in general terms, when we talk about aerosols, what we are talking about are solid or liquid particles dispersed and suspended within a gas. And aerosols are key to our understanding of the most important global challenges, including disease transmission, including COVID-19, air pollution and public health, climate change, and therapeutics and drug delivery. And so to address these global challenges, we must collaborate across disciplines and institutions to better understand particle properties and their effects. The work of my group spans across particle synthesis, characterization and measurement techniques, understanding particle dynamics, and the effects of particles and those on climate change and air pollution. In terms of particle synthesis, we generate particles for our experiments in the lab. We look at particles produced from combustion engines and from road transport and aviation. We're looking at characterizing the chemical composition of particles produced from peat burning and biomass burning. And we're also developing techniques to understand the charge state on aerosols, which is important if you want to manipulate the particles with electric fields. We're incorporating our understanding of dynamics into models, so here with computational fluid dynamics, and then we're also really interested in the effects that these particles have once they're released into the environment. And I'm going to talk a little bit more about a case study where we're looking at the effect that soot particles emitted from aircraft engines have an effect on contrails, these line-shaped clouds you see following the aircraft. And you can see them and observe them for yourself in the sky. So the formation of contrails is to a large extent controlled by the number of soot particles that are emitted from aircraft engines. And so a detailed understanding of the number and the properties of those particles is required to understand the following properties of the contrail. And what we've been able to do is simulate the emissions from all flights taking place over Japan, and we can do this for other airspaces, and therefore simulate the contrail that was produced from a particular flight and then its effect on climate change. So contrails have a warming effect because they trap outgoing long-wave radiation, but they can also have a cooling effect because they can reflect sunlight back out to space. And it's the balance of those warming effects and cooling effects that determines whether a contrail has a overall net warming or net cooling, and also the lifetime of the contrail is really important to understand because that determines the magnitude of that effect. So with our work, because we were able to identify and simulate in detail each individual flight, what we were able to show is that only 2% of flights contribute the vast majority of contrail warming effect. And what that means is that we can radically change the way we think about avoiding contrails formation and reducing the climate impacts of aviation. So we only have to deal with these 2% of flights rather than deal with all of flights that take place. And we can think about just minor changes to altitude, flight altitudes, that would have a really significant effect on those contrails. And so we're working on pushing this idea forward and thinking about how we can get this implemented, at least in a trial. So we're really interested to hear from you. We've got facilities for characterization of aerosols and opportunities for engagement with industry to co-sponsor and co-supervise PhD projects through our Centre for Doctoral Training in Aerosol Science.
Good morning, my name is Camille Petit. I'm a reader in the Department of Chemical Engineering, and today I'd like to give you an overview of what our group is doing towards accelerating sustainable materials development. To do this, I will use two potential examples of applications. One is molecular separation, so the separation between two or more molecules, such as for CO2 capture. If you look at the graph here, you can see that about 50% of the energy consumed by industrial processes is directed towards separation processes, and in particular, those performed by traditional technologies such as distillation. The idea here is to replace such technologies by others that consume less energy, such as, for instance, adsorption, and therefore the use of adsorbents. Another application is renewable energy production or solar fuel production. Here, we're looking at the reaction between water and CO2 to form a fuel such as methanol under the action of sunlight. So here we need a catalyst. You can see that in both cases, materials occupy an important role. The production of materials typically follow a linear empirical approach from design to pilot scale, and typically consideration about cost, processes, details come at a later stage, and therefore often one has to go back to earlier stage to improve on the process. So it can take years or decades from the concept of the material to its deployment. However, this approach has been useful for some applications, such as, for instance, oxygen-nitrogen separation and some photocatalytic application. However, it is not the most efficient approach because we have a lot of materials at our disposal. If we take, for instance, metal organic frameworks or MOFs, those are materials typically used for adsorption, in 2016, there were about 70,000 structures. So it's impossible to screen and test them in a linear fashion. So instead, we propose to follow a molecular engineering approach where we want to answer two questions. What is the best material? And more importantly, what does best mean? So here, we're considering not only the material's chemistry, structure, and simple performance metrics, but also the process type, condition, reactors. And we look at targets in terms of cost, energy consumption, resources usage, and that helps us identify a set of promising materials and processes that can be handled experimentally. So looking at a case study related to CO2 capture, here we have uptake curve for CO2 and nitrogen for two types of MOF, MOF 74 and UTSA 16. And by the look of those simple performance metrics, we can say that MOF 74 appears to be the best material for CO2 capture due to its much higher CO2 uptake. However, once we take into account process conditions and targets, we can see that in fact, MOF 74 is worse than UTSA 16 in terms of the purity of the CO2 it produces and the amount of CO2 it recovers, which are the two important process scale metrics. So molecular engineering, in summary, helps identify improvements compared to existing technology. It helps accelerate the implementation of new processes and materials. It helps identify adsorbents, for instance, for CO2 capture, direct air capture, pollutant removal, sensing, among other applications. And it helps define photocatalysts for solar fuel production, pollutant degradation, among other applications. So thank you all for your attention. I'll be happy to take any questions later.
Thank you so much, Jamie, Mark, and Camille for the great contributions and the inspiring talks. I'm Francesca Pietra, and I'm part of the Industry Partnership and Commercialization team at Imperial. Our team facilitates interaction between academia and industry by supporting the development of research collaboration with industrial partners and the commercialization of Imperial technologies. I really hope you are enjoying the event today. If you want to know more about what has been discussed or you are interested to engage with our academics, please get in touch. We'll be very happy to arrange a follow-up meeting to discuss in more details how we can work together. All the contact information are on the event page and are also being posted now on the chat. So please have a look. We're not going to have time now for questions, but please keep posting your question on the chat, and we're going to pick them up later during the Q&A session with Professor Mary Ryan. And now let's move on to the second part of the event. We have 3 tech pitches describing amazing technologies developed at Imperial to support and enable the transition to zero pollution. I hope you enjoy. Thank you.
Hello everyone, my name is Amir and I'm going to introduce you to a new molecule developed in our lab for detergent and personal care application. Our molecule is classified as a surfactant. Surfactants are the active and major component in home care, which account about 40% of the world's surfactant production, personal care, and other applications as textile, painting, and industrial cleaning. For this wide variety of applications, surfactants is a very huge market with an annual growth of 4.5%. Currently, the market is dominated by 2 main molecules, LAS and SDS. These can be evaluated according to 3 main properties: cleaning, solubility, and resistance to hard water. Regarding cleaning, LAS is much appreciated for its outstanding cleaning ability compared to SDS. But both of them are poor for what regards solubility and resistance to hard water. In order to overcome all these limitations, companies use formulations to obtain outstanding properties for the final product. But what formulation cannot account for is the sustainability of the surfactant. Indeed, LAS is an oil derivative, while SDS is much appreciated since it is derived from natural sources. Formulations needs to take into account also the requirements of three main entities. Developer, which require low cost of production with optimum performances. Consumer, with eco-friendly products and reasonable prices. And legal, with new toxicity and biodegradability targets. The challenges, however, is that additives must always be added, which increase the formulation cost and the environmental impact. And regulations are continuously changing, with new toxicity and biodegradability targets. Moreover, LAS and many additives are oil derivatives. Now, I would like to introduce you our new molecule, SAF, which stands for sulfonated alkyl furoate. Compared to the other two molecules, SAF has also very good cleaning ability, which matches the one of LAS. Regarding solubility, our SAF is soluble up to 140% in water without any formulation, while with LAS and SDS, the maximum surfactant concentration can be achieved is about 15% with a formulation. Has also very high resistance toward water without the addition of any additive, and is derived from natural feedstock. In this matter, we believe that SAF is the perfect compromise between consumer, legal requirements, and developer. It is also very highly scalable, since the synthesis procedure is quite simple. It's a low cost and delivers eco-friendly promises. As a perspective, imagine that you have 10 bottles of detergent. With our SAF, this can be replaced with only one bottle, which is translated in lower transportation cost, lower packaging cost, and lower CO2 emissions. The market is requiring eco-friendly products, which can match the same performance of the oil derivative ones. In this matter, we completed the lab testing and the IP, and we are in the stage of the customer discovery, with the aim to find a partner for the process scale-up, with the final aim to license the technology. I would like to take the opportunity to thank my collaborators, Raul and Jason, and all of you for the attention.
Hello everyone, I'm going to talk to you today about permanganate fuel cell technology. My name is Professor Anthony Kusinek. I'm Professor of Chemical Physics at the Department of Chemistry at Imperial College, where I've published over 160 papers on electrochemical energy systems and gained more than £25 million of investment in research as principal investigator. The innovation in my group has led to the spin out of 3 different companies, of which I'm co-founder, and here are the 3 companies which we've actually worked on. What I'm going to talk to you today is about a further innovation that's coming out of my group associated with transport and fuel cells and their use in transport. And one of the big drivers for that is the reduction in greenhouse gas emissions and also the reduction in noxious fumes such as nitric oxide. For instance, here we have a map of London and the emissions of nitric oxide. In fact, the fuel cell market over the last 4 or 5 years has been increasing very rapidly, and that's mostly associated with the significant rise in the use of fuel cells in transportation. And we can see that over the last 4 years that there's been a combined annual growth rate of 48%. Also, there's been a number of major fuel cell companies that have actually been bought out or collaborated with significant investors. In transportation, fuel cells are used in a range of different applications, typically for longer distance higher duty cycle applications such as trains, buses, trucks, material handling vehicles, and also cars. And one of the things that would actually lead to even greater uptake of fuel cell vehicles would be a reduction in the cost of their fuel cell stacks where the electricity is generated. At the moment, 50% of stack cost is associated with the platinum catalyst used within that stack. And that's where our innovation is associated. We call our innovation permanganate fuel cell technology, And what permanganate fuel cell technology allows us to do is not only reduce the amount of platinum, but increase the performance of the fuel cell. So this is the performance of a typical fuel cell, typical latter-day fuel cell, which looks a little bit like this. And when we utilize our permanganate technology, not only do we shift the curve up to higher voltage and larger currents, which leads to a more than twofold increase in power density, but we can also reduce the amount of platinum required by 70%. We also have other benefits as well, such as air-independent operation, and also the potential use of other fuels other than hydrogen. We view our advantage of our technology in terms of not only the improvement in power density, but also the overall reduction in cost of the system, where we think our systems could actually be half the price compared to current systems. And that's associated with the reduction in the cost of the catalyst, but also a reduction in the cost of ancillaries. Our long-term viewpoint is that we want to work with a number of companies in the fuel cell area in order to actually develop our technology and implement it in transportation applications. We see our development plan involves taking what we've developed in the laboratory and what we've actually filed a patent on, investing money in terms of either seed investment or Innovate UK type investment in order to actually build a stack, and to grow that to a stage where we can actually go for Series A investment with our collaborators and other potential manufacturers to manufacture systems on a larger scale. And so I'm happy to take any questions you might have.
Hello, my name is Dr. Alelia Kia. I'm a material scientist and engineer from the Department of Civil and Environmental Engineering. I'm also the founder of Permia, a research-focused spin-out company based at Imperial. My research covers the durability of cement-based materials, flood mitigation, and permeable pavements. Today, I will be talking about my new innovation, a high-strength clogging-resistant permeable pavement, which I call Kiacrete. Our world is more urbanized than ever. Our cities have expanded and are vulnerable to flooding. This flooding impacts lives and society as a whole. In the UK alone, the economic damage is estimated to be in the billions of pounds each year. A permeable concrete pavement, as shown in this photograph, is widely regarded as a cost-effective, sustainable drainage system that reduces the stormwater runoff and alleviates urban flooding. It is primarily used in low traffic areas and can improve stormwater and groundwater quality. The global market for permeable concrete is projected to grow to £18 billion by 2025. Existing permeable pavements have one major problem. They are susceptible to clogging from debris, as shown in this photograph. This clogging dramatically reduces the permeability to zero over a number of simulated cycles, as shown in this graph. Therefore, permeable pavements require regular, expensive, obstructive, and time-consuming maintenance. Even with this maintenance, over time, their drainage performance reduces until they can no longer allow water to flow through. In addition, they have low strength and can only be used for low load-bearing applications. My innovation overcomes these limitations. A conventional pavement is shown on the left, with indirect drainage paths that clog easily. Kiacrete, as shown on the right, has excellent drainage performance due to its direct cast-in drainage paths. On the left, the conventional permeable pavement is quickly overwhelmed by the volume of water introduced, whereas Kiacrete on the right is comfortably able to absorb the same flow indefinitely. The permeability of Kiacrete is 10 times as high as what is found in conventional unclogged permeable pavements. This graph shows that the permeability of Kiacrete does not reduce from exposure to debris over many clogging cycles, unlike the conventional solutions which clog dramatically over a small number of clogging cycles. Kiacrete's strength is almost twice as high as that measured in conventional alternatives, as shown on this graph. This means that Kiacrete can be used for the most demanding applications, including major roads and motorways, larger multi-story car parks, other major infrastructure, and even airport runways. The long-term goal of my research is for industry to adopt Qcrete for all pavements, to reduce the damaging impacts of flooding. I am currently working to develop my innovation into a deployable commercial scale solution with a number of industrial partners, including government agencies and airport operators. I have taken my innovation and scaled it up for delivery at a commercial scale. This involved developing a prototype delivery system, carrying out large-scale testing, and securing a viable site for long-term performance monitoring at Imperial's White City campus. This 9 square meter site allows me to monitor the long-term durability and drainage performance when exposed to real-world loading and weather conditions over at least the next 20 years.
And this is how my site currently looks like. Thank you very much for listening.
Thank you so much, Amir, Alalea, and Anthony for the great contribution. I hope you all enjoyed it. I am Michelle, and I am part of the IPC team at Imperial, supporting our academics to commercialize the technologies developed here via licensing or startup formation. If you are interested to know how to engage with our academics and get access to our technologies, please do get in touch after the event. We would be happy to discuss with you what we do and the support we provide for new partnerships and commercialization opportunities. Contact details are in the event page and also in the chat. You can also visit www.Imperial.Tech for more information on our technologies. It is now time for the Q&A, and I shall leave the floor to Professor Mary Ryan, who will chair the Q&A.
Thank you very much, and thank you to all of our speakers for those really interesting and diverse presentations. So I guess we all know that in order to deliver a transition to a sustainable society, we have to consider not just the technology, but the policy and the behavioral aspects. But just for today, I'd like us to focus on the technology and think about really what I'd like each of our panelists just to give me a very short answer on what they see are the major breakthroughs that would have really significant impact and the major barriers that's stopping us from doing that. So maybe if I go to Jamie first.
Hi everyone, thanks Mary. The issues that I was discussing are around the gas network and how we decarbonize it and what impact that has for the future. And there are a bunch of technology issues around improving the costs of hydrogen storage so that hydrogen can take the advantages that natural gas has had to this point in terms of being very a versatile energy vector. But there are also lots of things, advances that we can make in the modeling of those systems so we can plan them out better. And that's a particular area that Imperial has strength in, where we have at the Sustainable Gas Institute and across other parts of college, excellent capabilities from fine time scale and fine geographical scale modeling to understand how gas networks work and the other competing vectors like electricity networks, and also to understand how these things might play out on a much greater global scale using whole system global scale models to understand things like how hydrogen trade might work in the future and how you could have a hydrogen trade system that looks much like the gas trade system that we currently have, except not moving so much carbon molecules or implied carbon molecules around in the same system. So
okay. Mark, biggest innovation, biggest barrier.
Hi, Mary. So I think there's a lot to understand in terms of the properties of aerosols. We're only starting to understand how, for instance, some of these properties impact on health and the fate of particles in the human body. And specifically regards to the aviation contrails that I mentioned in the short video, we need to work across the industry with stakeholders to try and get that idea implemented. We need to work with, so we have a good understanding of the aerosol properties, their effects, but we need to work with people who actually sort of direct planes around the sky, airlines and the aerospace industry. There is a specific question in the Q&A. I don't know if this is the time to respond to that.
It's a very specific topic comes up.
Yeah, well, there's a question here. What is the impact or potential impact of sustainable aviation fuels on climate warming from contrails? And they would reduce the sustainable aviation fuels would likely reduce the amount of soot particles coming out, and that changes the contrail properties significantly, likely reducing the climate warming attributed to contrails.
So just for a little bit more context, what's the balance between the contrail effect and the CO2 effect from the aviation fuel? I guess that's also an interesting dynamic.
Yeah, absolutely. And so our understanding is that contrail effects are approximately the same magnitude, if not larger, than CO2. They're very different because CO2 has a very long lifetime in the atmosphere, whereas contrails last for a few hours up to a day. And so there's challenges in terms of bringing those two time horizons together in terms of policy. But overall, in terms of radiative forcing magnitude, our measure of how they affect the radiative balance of the Earth, they're on par, if not slightly larger than the effect of CO2 from aviation.
Wow. Okay. Camille, any thoughts on where the biggest challenge to innovation would come?
Right. So I think it will kind of relate to some of the point that Mark just made, in the sense that there is probably a need in a number of areas to join up knowledge at low and high TRLs. So industry would have more knowledge in some of the higher TRL areas versus academia will have more understanding of the fundamentals, and in some aspect there are technologies that would involve both sides, and having collaborations that joined up that would be nice. I think there is a demand actually from a number of academics to focus on critical questions that will have an impact, as we were discussing earlier, that are very specific. And so having access to actual important industrial questions is something that academics are ready to work on, and more globally, if I think of what we're doing in the separation area, but in other applications as well, having this holistic approach, looking at different aspects of a given problem rather than working in silo, really help accelerate some of those technologies. So I think that's the 3 points that I wanted to make.
It's interesting. I'm just going to jump to Anthony now, just because I know, Anthony, you've had a lot of kind of serial spin-outs and trying to develop technologies all the way from the lab up to application. Does what Camille say resonate with some of the challenges you've seen, and where do you think the blockages were in the technology adoption?
Yeah, I mean, I think that's you know what I've heard so far are, they're all quite reasonable comments. I think there is there are also issues that are associated with different technologies as well, of course. So most of my work has been done in the energy area, and what some of the other people have been talking about are sort of different areas. But I think in the energy area, the big issues are that you're actually talking about quite a long-term investment that has to go into those systems. So new technologies are always a difficult sell, in that sort of area. You've seen it, for instance, with wind, that wind has taken 30 years and now it's really taking off, but no one wanted to invest in wind at the beginning. So it's a tough sell. You have to be in there for the long haul.
Okay. And that's a particular challenge, given that we've got really urgent issues that we want technology adoption. Is there so you're talking about the barrier of long-term investment. Is there a way that industry, academia could work better and faster to maybe jump some of these TRL levels, or work in parallel?
Yeah, I think so. I think there probably are some really interesting possibilities there. So it's, of course, it's not just about the technology, it's about the engineering, and it's also about the manufacturing. If we're going to try and actually move quickly, then we need to manufacture at a very large scale. So really what you need to do is understand what's necessary to manufacture these systems at a large scale. And I think that's somewhere where industry can help massively. And also because there's going to be a significant change in industry as well. This is going to trigger a massive change in industry. So there's a possibility of industry helping there and actually retooling and moving to different technologies relatively quickly.
Okay. So Amir, I'm going to come to you, and I noticed there's a couple of very specific questions for you in the chat as well. So thinking about your surfactants, there's a question from Richard about the production costs compared to other competitors and whether there's toxicity data. I don't know if you've seen those, but if you could maybe comment on those as well and then talk about where you see the challenges in your space.
Yes, basically, I think the challenges that we have is a typical challenge of every chemical technology. What we are trying to do is basically using renewable feedstock, process it in a sustainable way and create a final compound that has properties that are equal or superior compared to the current one. I think that in our case, we are meeting all these targets. So we are starting to do the commercialization and finding a partner for this. Going to the question that you told me is partly related also to the commercialization. The market of the surfactants is actually a market which is dominated by high volume and low price. In our case, we cannot yet estimate the final cost of our surfactant, but we can say that the cost of the raw material quite competitive compared to the raw material used for LAS. So the production cost we will need actually to figure out the cost for the sulfonation and the cost of esterification, which is a two-step required to synthesize our surfactant. To be competitive in the market, we will need to reach a cost between $0.5 to $0.8 per kilogram. And to be honest, for now, we are quite confident that we can reach that price. Regarding toxicity test, we didn't still perform the toxicity test regarding our surfactant, but according to the chemical structure and comparing this surfactant to other molecules that have similar chemical structure, we are quite optimistic also that it's not going to be any issue regarding biodegradability and thermal toxicity.
Okay, and there's a very specific question here about what's your USP? How are you differentiated from a company that was started in the US called Cyrenex, which has a similar surfactant, renewable resource, good in hard water? What's unique about yours compared to that technology?
This is actually a very, very good question.
I guess we're looking for why yours is better, Amir.
Yeah. Basically, we believe, actually, we have looked on Cyrenex. Of course, we compare a lot our surfactant with their. I believe that they have a very, very good technology. What we believe we have a better selling point is that we are using feedstock that are actually cheaper. Fatty alcohol and furfural. Furfural is the cheapest building block green for furans. And the synthesis procedure that we have is also characterized by very, very high yield and low energy input. So I think this is the two main factors that actually are make our technology unique. And also the choice of especially the choice of the raw material are not particularly toxic compared to the furan used by Cyrenex.
Okay. Alalia, there's a question for you. How does your concrete perform in the winter in freeze-thaw cycles compared to conventional concrete? And where do you see the barriers to getting this fully commercialized and rolled out?
Sure. Thank you very much, Mary. So to answer that particular question, so we have actually performed a lot of tests, freezing and thawing tests on Kiacrete in comparison to conventional permeable pavements. And Kiacrete has performed a lot better. So it doesn't crack and it doesn't undergo any degradation. So it has superior performance for freeze thaw. And that's one of the biggest selling points for us, because the conventional systems not only have low strength and they don't have enough pore structure to absorb all water, but they also have a big issue in freezing and thawing, which this novel pore structure doesn't have. To respond to the other question in terms of the barrier, I mean, the UK targets of net zero emission by 2050 is very ambitious, especially for construction industry. So some of the key innovation breakthroughs to achieve these include using low carbon sustainable materials and building durable and resilient infrastructure. So in my own research field, a key breakthrough is this sustainable, resilient, impermeable infrastructure. It has low cement content, which is a critical greenhouse gas emission contributor and will reduce both of the harmful impact of flooding and the heat island effect. And it is resilient because it has low maintenance requirements throughout its long lifespan. However, there are always technical barriers that will need to be overcome. such as a change in mindset on both cost and industry-academia collaboration. Construction is highly cost sensitive, so projects are typically won by the lowest bidder and with little consideration of whole life costs. In my view, to overcome this, industry must choose long-term durability over initial cost. And also there should be more academic and industry collaboration to encourage innovation and widespread adoption.
Okay, so and I guess there's a strong policy element there, especially with the current replanning regulations that the current government are undergoing. Okay,
exactly.
So we've got a few questions that kind of relate to heating, decarbonisation of heating. So this is going to be a really big challenge for the UK to get to net zero, whether we can decarbonise heating. So what are the options? Can we get there in time? And then I guess a related question from Philip is, hello Philip, is around the idea that we used to have this town gas network that had hydrogen in the network already. Are there lessons to be learned from history about how we might move hydrogen around? So I'm going to come to you first, Jamie.
Yeah, okay, I'll take the first one first. So we can move energy into buildings by electricity networks, gas networks, and heat networks, although we use those less in the UK, but other parts of the world use them a lot. And then there are questions about what appliances you attach to the end of that network. And heat decarbonisation scenarios are very challenging, and many people would say that we are behind on our aspirations there relative to other sectors where we've maybe moved more quickly to get rid of carbon. It's definitely achievable, but there are lots of challenging barriers, and not just technological barriers, but public acceptance barriers. Heat pumps were, in scenarios at the beginning of this decade, the popular solution in scenarios to meet particularly domestic heat issues, but the deployment of heat pumps has been relatively slow, and proponents of hydrogen networks suggest that hydrogen networks might be able to work alongside electricity networks, providing a appliance at the end which burns hydrogen, which looks very similar to your gas boiler that you have currently, which might be able to get over some of those public acceptance barriers that have held back heat pumps. So in terms of what we might learn from the old town gas network, so that did carry quite a lot of hydrogen around, but it was a very much older network that the sophistication of the appliances at the end of that network wasn't nearly as challenging as it is now. 20% blending is maybe the maximum high volume that we might get to in a gas network before appliances attached to that gas network might start running into problems. And a project called High Deploy has been examining that at Keele University. But in order to get to the kinds of levels of heat decarbonisation that we'd really need, putting 20% by volume hydrogen into a gas network isn't going to get us anywhere near that. So you're really looking at getting very low carbon hydrogen at 100% in the gas network, and putting that into a very efficient appliances at the end. Heat homes is the way to go, and we don't learn that much from the.
Okay, so I'm going to jump to Anthony when we're talking about hydrogen. And if we were to go with hydrogen, clearly we've got a big scale-up challenge to create enough hydrogen. So where are the main, I guess, technology barriers to scaling up hydrogen if that was the option?
Well, you know, in the near term, of course, most of that hydrogen would be made by steam methane reforming. In the longer term, you know, our desire is to actually make that hydrogen from renewable energy sources and moving to water electrolysis. About 4% of hydrogen that's produced in the world nowadays is made from electrolytic processes, mostly in the chlor-alkali industry, actually. But what we'd need to do would be and it should be said that the amount of hydrogen produced in the world is actually quite large at the moment. But what we need to do is we need to sort of increase that by probably a factor of 10 or even a factor of 20. So the requirements are for large scale electrolysis over the longer term, you know, as we move away from so-called blue hydrogen to green hydrogen. Blue hydrogen where you sequester the CO2, to green hydrogen where you don't have any CO2 produced at all. And of course that requires low-cost electrolysis, water electrolysis. And there are two issues there. One of the issues is when you electrolyze water, you produce hydrogen and oxygen, and the oxygen doesn't have any value. So you just throw the oxygen away. So one question is, can you do something with that oxygen? or better still, can you move to a different electrolytic process that produces hydrogen and something else of greater value than just oxygen, which is what happens in the chlor-alkali industry at the moment, where chlorine and sodium hydroxide is worth much more than the hydrogen that's actually produced.
Okay, so I'm going to jump to a question from Kate, because we have been talking about zero pollution, but we've jumped back down into lots of details. And our zero pollution initiative, as Kate points out, is about taking a systems-based approach and trying to join up across different disciplines and technologies and application areas to try and get more of a holistic viewpoint. So maybe if I come to you, Mark, and talk about the Zero Pollution Initiative and where this systems-based approach can help thinking about relating to the work that you do in the future sustainability agenda.
Yeah, well, I mean, specifically on transport, we do need a systems thinking approach, because we have people or goods that need to be moved around, different technologies by which that could happen, different fuel vectors or energy vectors that we've heard about today that could be used. And if we just think about those in isolation, we are unlikely to find the global optimum or the global minimum. And in fact, we miss out synergies between coupling of different, say, behavioral patterns to different technologies. And so I think a systems approach is really necessary for something like transport, where you have the intersection of technology with society, and you want to kind of understand the best or most appropriate ways to achieve ambitious pollution targets or carbon targets.
Okay, so Camille, I don't know if you've got something to add there. Maybe a little bit, there's a question about, sustainability and supply chain, which obviously links to this systems-based approach, not just thinking about the system challenge from the technology perspective, but also from a local versus global perspective of materials usage.
Right, and also from the, I guess, the CO2 capture area, right? So if you think of CO2 capture, if you think of CO2 utilization, CO2 storage, there will be thinking to be done in terms of the location, in terms of synergies taking place, regionally or more globally, and that will have an impact also on, the technology that we involve for the separation to be done, or for the transport, or for the utilization. So all of this there will be indeed system thinking to be done from, for instance, a location point of view.
Okay, so I guess linked to that, so we've talked about, I guess, bringing in that local versus global initiative, and a lot of this work we've been talking about very Western-based challenges, but of course, to get to a sustainable future, we have to have technologies or adoption of different technologies that can be global. So what can we do to make sure that technological development also benefits developing countries to alleviate the climate crisis? Don't know who, Amir or Alilia, if you want to come in on that? No?
Sure, I am actually happy to answer that. So in particular for the permeable pavement technology, let's say, obviously flooding is a global problem. It's not just affecting West, as you mentioned, Mary. So it is a problem in India in particular, because they are exposed to a lot of monsoons. And the best way of getting interest would be through collaboration between the academia and industry, attending different events like this one, so that people can see the new research and innovation that is being carried out by the researchers. And we have recently, actually, by attending an online event like this, got interest from India, because they were exposed to a lot of monsoon flooding. And through that, we are hoping that we can collaborate with them to transfer this novel technology to developing countries like them, that they can hugely benefit from it. Okay. So I believe the key would be through contacts and networking and collaboration.
Okay, and Jamie, I know the Sustainable Gas Institute does a lot of work in trying to model transition in different countries. Is there something that we can bring to make sure that the transition is I guess, global and also just?
Yeah, I mean, one of the core activities of the Sustainable Gas Institute is the MUSE model, which is a global model, global whole systems model, and we've been involved in projects looking at gas corridors in India, gas use in Brazil, helping Vietnam with their indicated national decarbonization contributions. Yeah, and gas can play a role in a number of those countries, and particularly where existing infrastructure is there but could be utilized with less emissions associated.
Okay, so I guess the challenge is both to make sure that technology can be adopted globally, but also technology that we develop here isn't in turn exploiting developing countries, either through materials extraction or further pollution. Last, again, we're almost out of time already, but there's a few questions about training, and I guess one of our roles is both to do research innovation, but also to create the next generation of leaders. So what do we need to do, I guess, to make sure that we've got future fit scientists and engineers going forward, and within that, how we start to embed sustainability in the curricula? So maybe Camille and Mark, as you're very involved with the CDTs, might want to go. Camille, if you go first.
Yes, so I think it's important to have sustainability not so much as a single module, but something that would be across a number of modules to see how it's embedded in a number of not so much technology, but disciplines. And so this aspect, in addition to bringing on knowledge from the exterior as well, what is up to date in terms of what is being done currently, what is the future in terms of sustainability, and that I think are two key aspects. Yes.
Mark, anything to add?
Yeah, I'd agree with that. And in civil engineering, we have to include sustainability throughout the degree program for it to be a accredited degree course. That's at the undergraduate level. And then with the CDTs and PhD training, we have on our CDT, we have a management board which has representation from industry and the institutions that are involved, where those themes and what should be discussed and included in the training part of the CDT are shaped. So I think both at undergraduate level and graduate level, it's really important to get input from a range of stakeholders on what should be included on the curriculum.
And I guess just related to that, how do we make sure that our students are able to talk to industry? How do we give them enough exposure, I guess, to what industry needs, and also how they can develop personally?
Yeah, at the undergraduate level, I think it's really important that we invite industry in to give seminars and for careers events that are less, maybe not as formal as some, and we do that within our department with a lot of help from our student society in civil engineering. And then at the graduate level, I think having industry partners involved in projects with visits or placements, I think is a really important way. And a good way to foster that academic industry partnership and relationships.
Okay, good. I think that's the final word, Mark. And fortunately, it was a call to our industry partners to come and engage with our undergraduates and postgraduate students. So I hope you were all paying attention. So I'd just like to thank all our panelists for a really interesting set of talks and discussion, and for sharing their time and their thoughts with us. I hope you've enjoyed this event. Chris, you made a question in the chat about whether we will be planning other ones on different topics. Yes, we are. So if you've got some topics to suggest, please get in touch with our team. But if you want to hear any more about the work that we're doing, or to talk to any of the things you've heard today, or more generally, please get in touch with our industrial partnerships and commercialization team within our enterprise division. You'll have had the details when you joined up, but we'll be following up with information from the event. And just to thank all the people who have joined in for taking the time to share with us today. I hope we hear from you in the future. Thanks, and bye-bye.